Welcome to our comprehensive guide on visualizing linear relationships, specifically focusing on how to represent these with confidence intervals using Stata. This presentation will deep dive into Stata's two-way lfitci command, which is an invaluable tool for economic analysis. We will explore why it's crucial to visualize not just the trend in your data, but also the inherent statistical uncertainty. This guide is designed to be fully compatible with the latest versions of Stata, including Stata 18 and 19, as well as Stata Now. By the end of this session, you'll understand how to effectively use this command to create informative and robust visual analyses that go beyond simple trend lines. Let's consider a common economic scenario, the relationship between household income and food expenditure. We often observe that spending patterns become more varied at higher income levels. A simple regression line, represented by y hat, only shows the average outcome. This provides an incomplete picture by hiding the underlying variance and the limitations of our sample size. What initially appears as a clear trend can be misleading if we ignore the inherent risk. By adding the confidence interval, we gain the full context, visualizing the reliability of our mean estimate. For instance, a policymaker considering only the simple trend line might miss the increased uncertainty in spending behavior among higher income households, leading to less effective policies. The confidence interval reveals this critical information, guiding more nuanced decision-making. This workflow guides you in selecting the appropriate Stata command for visualizing continuous relationships. We begin by ensuring you have two continuous variables, y and x, and then consider if their relationship is theoretically linear. If the relationship is not linear, you would opt for quadratic fitting with qfit or smoothing with loess. If the relationship is indeed linear, you proceed to a linear fit and then define your analytical goal. For simply showing a trend, the two-way lfit command is sufficient. However, if your goal is to assess the precision of the mean estimate, which is critical for academic reporting, two-way lfitci is the gold standard. Lastly, if you need to generate a forecast range for an individual observation, you would use two-way lfitci with the stdf option. This systematic approach ensures you apply the most suitable command for your specific analytical objective. Let's delve into a comparative overview of Stata's fitplot commands. The lfit command provides a simple linear fit, showing only the regression line. It's best for basic trend visualization. Our primary focus, lfitci, enhances this by adding a shaded confidence interval region to the line. This is crucial for assessing the precision of your estimate, offering a more complete picture of the relationship. For nonlinear relationships, particularly those with a U-shape, qfitci offers a quadratic fit, also accompanied by a confidence interval. Finally, loess, or locally weighted smoothing, is a flexible tool for exploratory analysis. It generates a smooth curve without making strong assumptions about the functional form, but importantly, it does not provide a confidence interval. Remember that all these commands are part of Stata's powerful two-way family and can be easily overlaid with a scatter plot for full context. This comparison helps us understand where lfitci fits within Stata's broader capabilities. Now that we know what lfitci does, let's delve into the mathematics that create that important shaded region. To understand the lfit ciplot, let's briefly review the mathematical principles behind it. The visualization is based on the OLS, or ordinary least squares, model, where we predict a mean y hat based on our independent variable x. The shaded area in the graph represents the 95% confidence interval for the expected mean of y at any given value of x. This interval is calculated by taking the predicted value y hat and adding or subtracting the product of a critical t-value and the standard error of the prediction. Looking at the standard error formula, the term x minus xvar squared is critical. This term demonstrates why the confidence interval has that distinctive bow tie shape. The further an x value is from its mean, xvar, the larger this term becomes, which in turn increases the standard error and widens the interval. Think of a basketball player. Their shots are most consistent, or the confidence interval is narrowest from the standard free throw line, which is like the mean xvar. Shooting from farther away or closer, at the extremes, makes their accuracy vary more, resulting in the widest confidence interval. This mathematical model is powerful, but it relies on several key assumptions, which we'll explore next. For the lfitci plot to be reliable, our data must adhere to the core OLS assumptions, conveniently summarized by LINE. Linearity means the relationship between your variables must be straight. Fitting a linear confidence interval to curved data would be fundamentally misleading. Independence requires that each observation stands alone, unaffected by others. Normality specifies that the error terms should be normally distributed, a crucial condition for the validity of our confidence bands. Lastly, equal variance, or homoscedasticity, ensures the spread of residuals is constant across all data points. Violating these assumptions, such as forcing a linear model onto U-shaped data or data with a funnel-like spread of residuals, will produce an invalid and untrustworthy confidence interval. It is only when these conditions are met that we can confidently interpret the insights provided by our lfitci plot. This slide illustrates how we interpret the economic signals embedded within our confidence interval plots, using income versus consumption as our example. The slope of the regression line indicates the magnitude of the relationship. For instance, its steepness represents the marginal propensity to consume. You'll notice a narrow band around the center of the data. This signifies high certainty and precision in our predictions, as we have a robust amount of data points near the sample mean. Conversely, at the extremes of the income spectrum, the band widens considerably. This wide band signals significant uncertainty, indicating low precision where data is sparse, making predictions for very low or very high income households quite risky. Therefore, it's crucial to exercise caution. Avoid overinterpreting predictions if the confidence band fans out significantly, as the model's reliability diminishes in those regions. Understanding these elements is key to drawing valid conclusions from our economic analysis. Let's dive into the fundamental Stata syntax for creating our linear fit with confidence intervals. The basic command is twoway lfitci, followed by your dependent variable, yvar, and then your independent variable, xvar. However, for truly effective visualization, a crucial best practice is to always overlay your fit plot on a scatter plot of the raw data. This provides essential context, allowing your audience to see the underlying data distribution that informs the fit line and its confidence interval. To achieve this overlay, you simply enclose each plot command in parentheses within the twoway command, like this: twoway scatter yvar, xvar, twoway lfitci, yvar, xvar. The triple slash, 3 slashes, is merely for readability in your do file, allowing you to break long commands across multiple lines. For instance, if you're plotting food expenditure against income, your best practice command would be twoway scatter food expense, income, twoway lfitci, food expense, income. Beyond this basic structure, Stata offers several powerful options to customize the analysis, which we'll explore next. With the basic Stata syntax for lfitci established, let's explore crucial options for customization. The level option allows you to set the confidence level. For instance, level 99 will create a 99% confidence interval, resulting in a wider band. A key distinction is between stdp and stdf. By default, stdp calculates the standard error of the prediction, giving a confidence interval for the mean outcome, which is narrower. However, to forecast for an individual observation, you must use the stdf option. This accounts for individual level uncertainty, producing a significantly wider, more conservative prediction band. Think of it, predicting an average group outcome with stdp is different from predicting a single person's outcome with stdf. Additionally, ciplot option lets you customize the plot's visual style, and range option allows extrapolation beyond your observed data. These options enable precise tailoring of your visualizations. First, we load our dataset. Here, we use a dataset called food.dta, ensuring a clean workspace. Next, it's crucial to inspect the variables using describe and summarize. We need to ensure they are numeric and check for any missing values, which is a fundamental step in data quality control. Finally, and this is critical for creating professional-looking graphs, we label our variables. Stata automatically uses these labels for the axes titles, saving us time and making the graphs immediately understandable. As you can see in the Stata results, after running describe, the variables foodx and income have clear labels, weekly food expenditure dollars and weekly household income $100s. These will appear directly on our final plot. Now that our data is loaded, inspected, and labeled, we are ready to generate the plot. To begin our analysis, the crucial first step is data preparation. This involves loading our dataset, which in this case is food.dta. Once loaded, it's essential to inspect the variables. We use Stata's summarize command to get key statistics like means, standard deviations, and ranges for our variables, food expense, and income. Following this, the describe command helps us check variable types and ensure there are no issues. Crucially, we label our variables descriptively, as Stata will automatically use these labels for axis titles in our graphs, ensuring clarity and professionalism. As shown in the Stata output, we have 40 observations, with mean weekly food expenditure around $283.50 and mean weekly household income around $1,960. Now that our data is prepared, let's look at the complete Stata code to generate this publication quality graph. We use the twoway command to combine both a scatter plot of our raw data points and the lfitci command, which adds the linear fit line and its 95% confidence interval. After the primary commands, we apply several crucial options to enhance the graph's readability and professionalism. The title option sets the main title of the graph. We also use ytitle and xtitle to ensure clear and descriptive labels for our axes, reflecting the weekly food expenditure and household income. Finally, the legend option is customized to control the order and text for each element, ensuring that the 95% confidence interval, the linear fit, and the observed data are presented logically. With this robust code, we produce a comprehensive visualization ready for analysis. Now that we've generated our plot, let's analyze its visual output to understand the relationship between food expenditure and income. First, we observe a clear positive correlation. As household income increases, so too does their weekly food expenditure. The linear fit line clearly illustrates this upward trend. Next, we identify areas of varying precision in our estimates. Around the mean income level, the confidence interval band is notably narrow. This high precision indicates a confident estimate, primarily because we have a denser concentration of data points in this region. However, as we move towards higher income levels, the confidence band widens significantly. This low precision suggests that our estimate for food expenditure among wealthier households is more uncertain. This is often due to fewer data points and greater individual variation in spending behavior at the extremes of the income distribution. In conclusion, while our model effectively predicts average spending behavior across much of the income range, its reliability decreases considerably when making predictions for households at the very high or low ends of the income spectrum. This highlights a crucial point about the limitations of linear models at the extremes. So far, we've focused on predicting the average, but what if we need to forecast for a single specific household? This requires a different approach. Our scenario now shifts from predicting the average behavior of a group to forecasting for a single, specific household. This requires a different approach, captured by the stdf option. As you can see by comparing Graph A, which shows the mean prediction, with Graph B, the individual forecast, the stdf band is significantly wider. This is crucial because the forecast for an individual must account for two sources of uncertainty. First, the uncertainty in estimating the regression line itself, and second, the inherent random individual variance of a single data point around that line. For instance, predicting the average food expenditure for all households at a given income is different from predicting the exact spending of one particular household. the individual's unique choices add an extra layer of variability, leading to a wider, more conservative prediction interval when using STDF. After building our linear model, a critical final step is to perform diagnostics and validation. We must ask, was a straight line truly the right fit for our data? To answer this, we examine the model's residuals, which are the differences between our observed and predicted values. In Stata, the rvfplot command, used with yline 0, creates a residual versus fitted plot. Ideally, for a well-specified linear model, these residuals should appear as a random cloud of points scattered evenly around the zero line, indicating no systematic patterns. However, if we observe a U-shaped or curved pattern in the residuals, it signals a nonlinear relationship that our linear model isn't capturing. In such a case, we should consider switching to a quadratic fit, such as using the two-way qfitci command, which was mentioned earlier. Another common issue is a funnel shape, where the spread of the residuals either increases or decreases across the fitted values. This pattern indicates heteroskedasticity, violating a key assumption of ordinary least squares regression, suggesting our standard errors and confidence intervals might be unreliable. We've covered a lot today, so let's consolidate the key takeaways and best practices. The primary purpose of using the lfitci command is to reveal both the direction, or slope, and the precision of a linear relationship through its confidence interval. A crucial best practice for proper context is always to overlay your lfitci plot with a scatter plot of the raw data. This allows your audience to see the underlying data distribution. When interpreting these plots, pay close attention to the distinctive bow tie shape of the confidence interval. Wider bands indicate greater uncertainty, which is often a result of less data or higher variance at those points. Lastly, remember the difference in syntax for your analytical goal. Use the default stdp for predictions of the mean average and the stdf option when you need to create a wider prediction range for individual observations. A good rule of thumb is to never present an lfitci plot without the accompanying scatter plot. Without the raw data, your audience can't independently judge the appropriateness of the linear fit.